Let's walk through the Unit 3, Chapter 3 test review on curve sketching and optimization. So number one, a t-shirt maker estimates that the weekly cost of making X shirts is given by C of X. The weekly revenue from selling the shirts is given by the function R of X. And part A is saying what is the profit of all the shirts made if all the shirts made were sold. So if we think about profit, profit is just revenue minus the cost. And so we have R of X, we have C of X that represents revenue and cost. We just subtract those two values. And then we have P of X to represent profit. So now part B, what is the maximum weekly profit? So if we want to find the maximum profit, we can find the rate of change or find the derivative so that we can figure out where the rate of change of the profit will hit a zero, will hit a maximum value. So then we just find the derivative and set that equal to 0. So 18x becomes 18. 50 goes to 0. The x squared comes down in front, gives us 2x times 9 over 200. And then we set that equal to 0, and we solve for x. We get 18 is equal to 0.09x. X equals 200 shirts. So now, if we want to find the largest maximum profit will occur when 200 shirts are sold, and that profit will be plugging 200 back into P of X, and that'll give us $1,750. Okay, number two, the derivative f of x has zeros at x equals a and x equals c, and a minimum at x equals b as shown. The function f of x is concave up. So this is the second derivative function. And if we're looking at the second derivative function, we have to think about what the y values represent, right? The y values represent concavity. So anywhere that the graph sits above the x-axis represents concave up. Anywhere that the graph sits below the x-axis represents concave down. So we know the critical points are at A and C. Those are our potential points of inflection. And then to the left of A, we see the graph sits above the axis, so we know this is going to be concave up. Below the axis, concave down. Above the axis, concave up. So based off of this, we know the answer choice must be when x is less than A and when x is greater than C. That will be when the graph is concave up. In this region to the left of A and this region to the right of C. Okay, number three, verify whether the function f of x satisfies Rolle's theorem on the interval 0 to 4 and find all the numbers C that satisfies f prime of C equals 0. So with Rolle's theorem, we want to be able to guarantee that somewhere between the endpoints, we have another point where the slope is 0. So to do that, we have three conditions. First, we need to make sure the graph is continuous on the closed interval, differentiable on the open interval, and finally, the endpoints produce the same y value because we want the endpoints to produce an average slope of 0. So we have a polynomial function, so we know that the function will always be continuous on the closed interval, differentiable on the open interval. That will always be the case with polynomials. And now we look at the endpoints. So we plug 0 and 4 back into the original function. And when we do that, we get y values of 1. They're both equal to 1, which means that if we do change in y over change in x, if we find the slope between these 2 points, we're always going to be guaranteed a slope of 0 because our y values have the same y value, have the same value. Okay, so we just want to figure out the x value where the slope is equal to 0. Okay, so we find our derivative, set that equal to the average slope, which in this case will always be 0. So 3x squared becomes 6x, negative 12x becomes negative 12. We set the derivative equal to 0. We want to find out when is the slope going to be equal to 0. Solve for x, x equals 2. Now, we also want to make sure that our value sits in the open interval of 0 and 4, and 2 does fall between 0 and 4. So we have the x value where the slope is 0 on the graph. Okay, number 4, which of the following statements is true about the function y equals x to the 2/3? So all this, some of these are referring to the first and the second derivative, so we have to go and find those functions. So we go through and find first derivative function, going through power rule. So x to the 2/3 becomes 2/3 x to the negative 1/3. We clean this up, we get 2 over 3 x to the 1/3. Critical point is at 0. And then we plug -1 into the derivative, we get a negative value. Plug 1 into the derivative, we get a positive. So we know the graph is decreasing, hits a minimum, and then starts increasing. Notice, however, that the critical point is coming from the denominator. So we know that this 0 exists on the original graph, which means that the graph is going to be connected, but because it is part of the denominator of it is a critical point coming from the denominator of your derivative, we know that this is where slope does not exist, and so this will be where either we get an undefined slope or we get a sharp point. So we know that the slope here is undefined because the critical point is coming from the denominator of your f prime. Okay, we move on to second derivative. So we go through power rule again, bring down the negative 1/3, subtract 1 from the exponent, we get negative 2 over 9x to the 4/3. Again, the critical point is 0. Plug -1 into the second derivative, we get a negative. Plug 1 into the second derivative, we get a negative. So we get no point of inflection because there is no change in sign at x equals 0. Okay, so let's look at our choices here. Which of the following is true? There is a critical point at 0, 0. That's true. We found those critical points. F prime and F double prime are undefined. That is also true because those are critical points that come from the denominator. And if we plug 0 into the derivative function, we're going to get 2 over 0. Into the second derivative, we'll get negative 2 over 0. So that tells us that those values are undefined for f prime and f double prime. The curve is concave up over the interval from 0 to infinity. So from 0 to infinity, we can obviously tell this is concave down, so we know this is false. The curve is concave down over the interval from negative infinity to 0. We see concave down from negative infinity to 0, so that's true. So our answer choices that will reflect the true values will be the first, the second, and the fourth. So answer choice B. Okay, let's look at number 5. The graph of the function g of x is given. So we have a graph where we want to find critical points so that we can determine the graph of g prime. So we're going to try and create our g prime graph. So that means we are going to be looking for our critical points, basically coming from the max and the mins. So we put those on the sign line. To the left of 3.5, we see the graph is increasing. To the right is decreasing. And then to the right of 6, we see the graph is increasing again. So something that we have to be careful about is that here we see the slope is undefined. So we know that this point will not exist on the f prime graph because f prime graph describes the slope at every point. So we're going to be getting a negative value, a negative slope, turning all of a sudden to a positive slope. So there's going to be a sudden change between negative and positive value. Okay, and also another thing to notice is that the slope here is increasing at a constant rate. So if this is a slope of, let's see, if we look at this graph here, up 2 over 1, up 2 over 1, this is a constant slope of 2. So this So on the derivative graph, we're going to be expecting a y value or slope of 2 that is consistent from 0 to this x value of 2. Okay, so if we look at our answer choices, we're looking for a portion of the graph that sits above the axis to the left of 3.5. So that's going to eliminate A, that'll eliminate C, that'll eliminate D. So we're down to choice between B and E. Now, what we do know is that the slope does not exist at 6, so we should have an open circle at that point. Here you see there's no open circle, so it has to be part E. Now this may look a little strange because we see that the graph doesn't extend down. The reason why is because there's a constant slope of 2, so it's holding that y value of 2 all the way throughout, and then the slope becomes more gradual, hits a maximum, starts decreasing, hits that sharp point, and all of a sudden after that sharp point it'll begin holding a positive slope of 1. So we see that with the positive slope of 1 over here. Okay, number 6, the height of the object after t seconds after it is dropped from a height of 500 meters is given by h of t. Find the average velocity of the object during the first 4 seconds. So average velocity is simply going to be the change in position over the change in time. So we're just going to find the slope between the endpoints, and the endpoints is given with the 0 second and the 4th second. So we plug 0 and we plug 4 back into the position function. So this should actually say x of 0 and x of 4. We get 500 and 421.6. We simply find the change in y, change in position over the change in time. That will give us the average velocity. So once we find the average velocity, that'll be our answer, which was negative 19.6 meters per second. Okay, part B, used MVT to verify that at some point during the first 4 seconds of the fall, the instantaneous velocity equals the average velocity. So mean value theorem, we have the average velocity. We should have to set the derivative function equal to the average velocity, solve for x to figure out where on the curve is there going to be an instantaneous rate of change that will match this exact negative 19.6 slope. So to find the derivative, we simply look at our function here. We can go through power rule, bring down the 2, we get negative 9.8t. The 500 is constant, that will go to 0. So then we set our derivative function equal to the average slope. Now we simply divide by negative 9.8. We get t equals 2 seconds. And it says find the time and find the height. So the time is 2 seconds. To find the height, we simply plug 2 back into the original position function. So plug 2 back into x of t, and we're going to get 480.4 feet. Okay, number 7, Max plans to build 2 side-by-side identical rectangular pens for his pigs that will enclose a total area of 216 square feet. What is the minimum length of fencing he will need? So we're trying to optimize, trying to find the minimum perimeter. So we're trying to optimize perimeter, and we're going to use area to help us rewrite our equation in terms of just one variable. So we have our rectangular pen here with two identical pens. And I'm going to call the horizontal x, I'm going to call the vertical y's. So my perimeter is 2x plus 3y. Area is width times height, x times y. Now if I want to find the area, well, we know the area, which is given to us, 216 square feet. So we're going to be solving for one variable, plugging into the perimeter equation, and then finding the derivative for p. So I'm going to choose to solve for y. Y equals 216 over x. Plug this back into the perimeter equation. So we get 2x plus 3y, and the y value is represented by 216 over x. We clean this up, get this to a form where we can apply the power rule. So then once we have everything in the numerator and set up ready to go, 2x, we find the derivative, so 2x becomes 2. 648x to negative 1, we bring down the negative 1, subtract 1 from the exponent, and then we just set our derivative equal to 0. Okay, when we do that, we simply solve for x. We get x squared equals 324, so x equals 18 feet. Now, if x is 18 feet, we're going to plug 18 in for x to solve for y, so y is 12 feet. And it says, what is the minimum length of fencing? So we want to find this value for perimeter. So we plug 18 and 12 back into the perimeter equation, and we solve for p, and we get 72 feet, which will represent the minimum amount of fencing that will produce this area of 216 square feet. All right, number 8, a manufacturer wants to design an open top box having a square base and a surface area of 80 square inches. What dimensions will provide a box with maximum volume? So we can tell that we're trying to optimize the volume equation. Okay, so to do that, we're going to have to use our surface area equation to help us get rid of this h from this volume equation. We want the right side to be in terms of just one variable. So surface area, we're just going to be adding the areas of the 5 faces of this open top box. So the base is x squared, and the vertical heights will be x times h, and we do that 4 times, so 4xh. The surface area is 80 inches. So we can just simply solve for h by subtracting x squared, dividing by 4x, and then replace the 80 minus x squared over 4x replace h with this expression in terms of x. So we can clean this up, distribute the x squared through, divide the 4x, split up into individual terms. So we get 20x minus 1/4 x cubed. We find the derivative, set that equal to 0. We want to find when is the rate of change of volume going to be at its greatest. So we set the derivative of volume equal to 0. We solve for x, and we get x squared equals 80 over 3. Solve for x, we get root 80 over 3, which can be approximated to be 5.164. So we plug to find the maximum volume. We're going to plug this back into the surface area equation to find the height. And to find the height, we get 2.582 inches. And so the maximum volume, by plugging in the x squared and the h, we get 68.853 cubic inches.